Hey everyone, welcome to this video. This is part one of convolutional neural networks. So a quick review. In a fully connected layer, perceptrons are connected with a weight to all perceptrons in the next layer, as you can see in this picture here. The perceptrons are in fully connected layers. And here is how we previously classified images. We previously used a fully connected feed-forward neural network to classify images, and the perceptron in hidden layer 1 have 784 weights each. So we worked with an image of 28 pixels by 28 pixels, which we flattened to one dimension, and 28 times 28 gives us 784 pixels. So here is the model we previously ran in the course, fcffnn.ipynb file. Images are 28 by 28 pixels, which we flatten right here. And we take into account the 784 pixels. But are images commonly 28 by 28 pixels? You might see an image that's more along the lines of 1280 pixels by 720 pixels. And the perceptron in hidden layer 1 have 921,600 weights each. That's almost a million weights each. That's too many parameters. What's the issue with that? Long training time, which means it's going to cost you more money, and you risk overfitting. Plus, when you flatten the image from 2 dimensions to 1 dimension, there's going to be some information loss, which isn't ideal. What's another issue with using an FCFFNN for classifying images? A FCFFNN would not be able to take location into account, such as when this face is in the upper left-hand corner versus the bottom right-hand corner. Ideally, we want to recognize something regardless of location. For recognizing things, we don't look at everything or every pixel. We look at features. You can probably tell that this is a picture of me or human face, not because your eyes are scanning every single little pixel in this picture, but because you can notice like the hair, the forehead, the eyes, the nose, the mouth. Your brain notices these features quite quickly and can tell this is a picture of a face. So yeah, some common features that you'll recognize are like eyes, hair, and mouth. And how do we extract features? We use a kernel/filter. You can think of this kernel/filter as a feature extractor. So we have a horizontal kernel, it will extract horizontal features. If we have a vertical kernel, we will extract vertical features. So in the horizontal kernel, horizontal features such as my shoulders, my eyebrows, my eyes, and my hairline are quite noticeable. Whereas for the vertical kernel, like the buttons on my shirt and my ear, or more specifically, my right ear, is more noticeable. So what do these kernels look like? They're just numbers. At the end of the day, AI and like deep learning is still math being done. So the kernels are just a bunch of numbers. Here's a vertical 3 by 3 kernel, and here's a horizontal 3 by 3 kernel. And this kernel is used in convolution for a convolutional neural network. Think of this kernel as like an overlay that we place on top. And then we do some multiplication and addition. So we do 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 0 plus 1 times 0 plus 1 times 0 plus 1 times -1 plus 1 times -1 and then plus 1 times -1 here, which, as you can see in this quick summarization of the map, gives us 0. So now our feature map will have this 0 in the upper left-hand corner. We'll move this kernel down 1, do the math again, which gives us a 3. We'll put a 3 here. And once we're done, this is what the feature map looks like. And now you're probably thinking, why do I care about this feature map? Because When we put a face kernel as a simple example to this image of a face, the feature map will highlight that the face is in the upper left-hand corner, whereas if we apply this face kernel to this second image, the feature map will highlight that the face, is in the bottom right-hand corner. So using like convolutions and kernels, yeah, using convolution and kernels, we are able to overcome this weakness where FC, FF, and N would not be able to take location into account. And in a convolutional neural network, there is more complex feature extraction as the layers progress. So in the early layers, we have very basic feature extraction, like some basic lines, a dot, these like half circles or like semicircles. But as the layers progress, we have a kernel for an eye and a kernel for a nose. And this eye is constructed from the semicircles and the dot. And this triangle nose is constructed from these three lines here. So just remember this. More complex feature extraction as the layers progress. Now for kernels, again as a review, a kernel/filter is essentially a feature extractor. And a 3x3 kernel has 9 weights. These kernels are not set by us. It's not like we handcrafted an eye kernel and we handcrafted a nose kernel. They are learned by the network. I want you to focus on this 9 weights part. Even though we're learning about a different architecture for deep learning, at the end of the day, this weights part, this is still what is going on behind the scenes, where we have a model with weights. It gives an output or prediction. We tell the model how correct or incorrect its output or prediction is. That is used to update the weights so that we hopefully have better weights, so there's better outputs / predictions, and we have a lower error / loss. Okay, that's the end of this video. In the next video, we'll go over part 2 of convolutional neural networks. Thanks for watching.